In this video, I will talk with you about linear regression. And the first case we talked about is univariate linear regression. In finance, linear regressions are commonly used to describe the returns of an individual security, and we call this independent variable compared to the returns of the market, and we call this independent variable. Now let's look at an example. Given a training dataset with m training instances, and there are market returns of S&P 500 and the security return. The task is to compute a function that takes the market return as input and the security return as the output. Now let's call h of x parameterized by theta the hypothesis function giving the return of the security A. And x here is the return of the market. The parameters theta naught is the intercept of the regression line, and theta 1 is the slope. So this is the hypothesis function with one variable. And because this is a regression with one variable, so we call this univariate linear regression. So given the training set, we need to fit the regression line to the data, and we measure some cost for this, and the cost must be as minimal as possible. Now we talked about the cost function. We need to fit the line to the training data points. So here we form a cost function, and the cost function is some sort of a function that measures the difference between the estimated and the target value for each training data set. For each training data point. So this is the ith training data point. You take the difference and then square it and take a sum for all the training data points from 1 to m. This measure is averaged by divided by m, and the 1/2 here is just to facilitate the computation, because later on we take the derivative, and that power 2 here would be cancelled by that 1/2. That's the reason. The cost function is the function of two variables, theta naught and theta 1. And you need to find theta naught and theta 1 such that the cost is as small as possible. Now first look at a special case for the illustrative purpose. Let's assume theta naught equal to 0. So to form this cost function, we can see that the cost function is the function of theta 1. So the cost function would look like this. And we need to adjust theta 1 such that theta 1 moved toward an optimal point, and it repeats again and again, and this loop repeats until the algorithm converges. So first let's assume that we start from a point from the right side of the optimal point, let's say from here. We can see that the gradient is positive. So on the right side of the quadratic function, gradient is positive. So the update by negative alpha times the derivative, the partial derivative of the cost function with respect to the parameter theta 1 is negative, and here we assume alpha, which is the learning rate, positive. So this whole thing is negative, and from there we can see that theta 1 moves this way toward the optimal point, theta opt. Now let's say we start from a point from the left of theta opt. Then you can see that the gradient on this side is negative, and the update by negative alpha times the partial derivative of the cost function with respect to theta 1 is positive. So from here we see that theta 1 moves toward theta opt. So iteratively theta 1 moves toward theta opt. So again and again we update theta 1 such that it gets closer and closer and closer to theta opt. And when the change between two consecutive steps is very small, becomes very small, or the number of iterations is greater than a specific number, then we say the conversion, the algorithm converges. And at that time, theta 1 is right here, very close, or right at theta opt. What if we start right at the minimum? So if we by chance select theta 1 equal to theta opt, then the update is always 0, as there's no change in each iteration. Now we assume that theta naught is not equal to 0, so we have both theta naught and theta 1 in the hypothesis, and the cost function is now a two-dimensional function, and J is a function of both theta naught and theta 1. So if we plot the cost function against theta naught and theta 1, it looks like this. And the global minimum is somewhere here. And at the same time, we plot the contour plot. So the contour plot contains the eclipse with different colors to express different costs. And points on the same eclipse have the same cost. So for example, theta naught and theta 1 on the blue eclipse gives the same cost, and you want to get to some theta naught and theta 1 that give the minimum somewhere here. Now for this case, we look at the gradient descent update rule again, and now we repeat, and in each iteration we do this for both theta naught and theta 1. So previously we repeat this for just theta 1, and now we have both theta naught and theta 1. We adjust theta naught and theta 1 iteratively, and in each iteration we subtract theta naught by that much, which is alpha times the partial derivative of the cost function with respect to the parameter theta naught, and we adjust or update theta 1 by subtracting alpha times the derivative of the cost function with respect to theta 1, and we repeat this again and again until the convergence. And alpha here is the learning rate, and we specify this. And this controls the step size. And if alpha is too small, then it takes long to converge. But if alpha is too large, and the algorithm may fail to converge. And it's important that you need to update the parameters theta naught and theta 1 simultaneously. The reason is, let's say if you compute the new value for theta naught and store it into theta naught, then at that time theta naught will change. So the cost function is changed accordingly. That affects the computation of theta 1. And if you have more parameters, then it affects all other parameters, theta 1, theta 2, etc., etc. So in order to do this, you got to store the new updated value into a temporary variable. So you got to store to a temp variable, and this is done for each parameter. So then after this, then you update so you got to remember this. You got to update the all the parameters simultaneously, and you have to specify the learning rate carefully. If it is too small, then it takes long to converge, and otherwise if it is too large, then it may be diverged instead. And this actually is summing up some notes that we talked before. Regarding the convergence, the closer to the global minimum, then the smaller the update is. And we say the algorithm is converged if the changes between the two consecutive steps is smaller than a very small value, and at the minimum the gradient is equal to 0 or approximately equal to 0. Now look at the gradient. So from the previous slide, this is the cost function. So first look at theta naught. The partial derivative of the cost function with respect to theta naught is equal to this. And notice that x with superscript 0 is actually equal to 1 in the hypothesis. And here actually I have to add the subscript 0. So each any point looks like this. Each shading point is a vector x with x0 and x1. x0 is actually 1 because you have just one single variable, right? This algorithm is also called the batch gradient descent because we look at all the training set, For theta 1, similarly, the partial derivative of the cost function with respect to theta 1 is this. And there is a typo in the formula, so all the superscript here are actually I. So I made a correction, as you can see. And I, meaning the I instance, or the I samples, the I examples. And in general, you may want to write the hypothesis as a linear combination of, for example, theta naught times xi naught plus theta 1 times xi1. So when you take the derivative with respect to, let's say, theta naught, and what you have left is just xi naught, and that's why you have the xi naught here. And similarly, if you take the derivative with respect to theta 1, then what you have left is just this, and that's why you have that term there.